Good morning, everybody. Welcome to another colorful and exciting morning of chemistry, Chem 1211, with your host, me, Dr. White. If you notice, when I do that, my eyes open up more. Must be a reflex action. But, anyways, we're going to have an exciting morning. Let me explain what we'll be doing today. First of all, I'm going to be going through problem set 9, both part 1 and 2. Then we'll do our lab, which is going to be really explosive today, really explosive. And then I'm going to have you go to breakout rooms for about 15 minutes or so in order to meet your colleagues and also give a chance for you to talk to me one on one or in a small group. And I'll get a chance to meet you. I did that yesterday and it worked out well. And I'll be reordering the breakout rooms so you get a chance to meet new people. And a couple of things I should mention. One, uh, hopefully by Sunday, I have to redo Monday's lecture. I've been swamped this week, so I haven't had a chance. And that happened last semester too when I had technical difficulty because the video didn't turn out. And I'll redo that. Yes, I can do that. And I'll post it. And by Sunday afternoon, I'll have caught up Monday's lecture from this week, Wednesday's. Those people who had lab yesterday, I'll have posted. Excuse me, oh, a little itch there. And then I'll have your lab today posted. All that will be by Sunday. Speaking about posting, a little while ago, I posted the scores, lab scores for your lab, I believe number 3. Don't forget, hand in the lab today. Make sure you get caught up because next Monday, I talked about it last Monday, but I didn't stress it. Over the weekend, I'll send out an email telling you get caught up because you got to keep on track. It makes my life easier. That's not even right. Doable. So I don't have a ton of labs or trying to track down, well, did you email? Did you do this? Get them in on time, please. And with that, let's go to practice problems for chapter 9. All right, thumbs up, people. Do you see chapter 9? Thank you. All right, now let's look at question number 1. Write the electron configuration for. All right, before I do this, let's go to my whiteboard. Everybody see the whiteboard? Thank you. All right, let's do some important things that you should know how to use. First of all, when we talk about electron configuration, we talk about shells. And a shell is a place where electrons have approximately the same energy and are approximately the same distance from the nucleus. Remember, the nucleus is the center of the, hold on one second. Let's move it over here. So you have the electrons in the shells. Now, shells have very difficult names. 1, 2, 3, 4. Now, in each shell, there are subshells. And the subshells, you'll find electrons that are exactly the same distance from the nucleus with the same energy. And it's important to know the number of subshells in each shell. And this is real difficult. Shell 1 has 1 subshell. Shell 2 has 2, 3 has 3, 4 has 4. So shell 1 has 1 subshell, shell 2 has 2 subshell. Wow, it's a tongue twister. 3 has 3 subshells, and shell 4 has 4 subshells. Now, when we talk about the shells, shell 1 has the lowest energy. As you go down the list, shell 4 has the highest energy. And because of stability and how Mother Nature set it up, Mother Nature being the greatest of all chemists, you always fill the lowest energy shells before you go to the next energy shell. So you start with 1, then fill 2, 3, and 4. Now, when we talk about subshells, there are 4 of them: S, P, D, and F. S, you can put the maximum number of electrons is 2, P, 6, D, 10, F, 14. Can you keep a secret? Because my little gift to you that you only have to know electron configuration up to magnesium, atomic number 12. You don't have to know about D or F's subshells. Just S and P will be enough for my class. Remember, it's a secret. So we now know we have shells, know the number of subshells, and the subshells have letter names, S, P, D, and F. Here's the maximum amount. And also for the subshells, S is the lowest energy. As you go down the table, F is the highest. And you always fill the lowest energy subshell of a shell before you go to the next lowest energy subshell in a shell. And now if we go back and look at the first one, write the electron configuration for nitrogen. Well, how do you do that? Well, the first thing you have to do is find out how many electrons you have. And how do you find that? You look at the periodic table, which you learned for test number 1, that the atomic number, the number right here in the upper right-hand corner of this periodic table box, tells you how many protons and how many electrons. So if we're going to do the electron configuration for nitrogen, it has 7 electrons total, and therefore we have 7 to put in. Well, you start with shell 1 and its subshell. There's only 1. And remember, a subshell is named by a number and a letter. Subshell, named by a number and a letter. So the first subshell for nitrogen that you can put electrons in is 1s. How many electrons can you put in an s orbital? And the answer is 2. Now, how many orbitals, or how many, as subshell is 2. How many subshells does 1 have? 1. And we filled it up because you can only put 2 electrons in 1s. So now we have to go down this list to the next highest and lowest energy shell, that's 2. Notice it has 2 subshells. What's the lowest or first energy subshell of shell 2? And that's shell, subshell is a number and a letter, and that would be 2s. How many electrons can you put in any s orbital? And the answer is 2. Well, 2 plus 2 is 4, but we have to get to 7. So are there any more subshells than 2? And the answer is yes. We've used 1, and there are 2 of them. And the second one is 2p. Remember, subshell is a name, is a number, and a letter. 2p. How many can we put electrons in 2p? 6 max, but if you notice, we have 7 electrons. We've accounted for 4, and that means we have 3 more to go, and we'll put it in there. And therefore, the electron configuration for nitrogen is 1s2, 2s2, 2p3, 7 electrons. If you look through here, I have a number of them. Let's have you try one. I want to share the fun this morning. So why don't you try write the electron configuration if it was on a test, 3 points each. Magnesium, and on a test, I give you the name, not the chemical symbol. And I'm going to help you out because you may not have a periodic table handy. If we look here, magnesium, how many electrons does it have? It has 12. And therefore, I'm going to really help you out. You have 12 electrons. And I'm going to move this up so you can see this table. Both of these tables will be given to you in important information for test number 2. In the past, I used to ask students to memorize this. Now I don't. Have fun. Now, I've always been debating with myself, should I get a digital recording of game show music to play at times like this, like The Price is Right or whatever other ones are on TV. I have watched those in eons, but dun, 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 nah. And for all of you who have your webcams off, if you had them on, I'd be smiling because I'm seeing you now work on chemistry and hopefully having fun. Let me do one thing real quick. For some reason yesterday, my video recording shut off, so I'm going to check it every once in a while. And when you're done, give me a thumbs up. See, a lot of people are done. All right, I'll give you another 8.7 seconds. 8.2, 8.4, 8.6, 8.62. Time's up. Let's do it. And the question is, write the electron configuration for magnesium. So how do you do that? Well, what's the first shell you'd put electrons in? One. One has one subshell, and that, remember, you always fill lowest energy first before you go to the next cell, and also before you go to the next subshell. So shell one has the subshell 1s. Remember, a subshell name is a number and a letter, and the maximum amount of electrons we can put in there is 2. And we've now filled up shell 1 because it's only got one subshell, and we filled it up. So now we have to go down to the next lowest energy shell 2, and it has 2 subshells. What's the lowest energy subshell in shell 2? Ooh, say that 10 times quickly. No, don't. Is 2s. And again, you can put maximum of 2 electrons in any s subshell. Well, 2 plus 2 is 4. I've got to get to 12. I better get moving. Well, how many subshells does shell 2 have? 2. What's the second one? First one is 2s. Second one is 2p. How many electrons max can we put into a 2p or any p orbital? And the answer is 6. Well, subshell name is a number and a letter, and I can put in 6. So now I have 2 plus 2 plus 6. I'm supposed to do 12 electrons. I have 10. Ooh, I got 2 more to do. Well, how many subshells does shell 2 have? 2. Well, guess what? I filled them both up. So now I have to go to the next shell, and that's shell 3. What's the lowest energy subshell in shell 3? 3s. And how many electrons can I put in there? 2. So I'm at 3s, and I'll put in my 2 electrons, which means 2, 4, plus 6 is 10, plus 2 more is 12. I'm done. And the electron configuration for magnesium is 1s2, 2s2, 2p6, and 3s2. Now, chemists use this knowledge to understand how elements form molecules. Now, it turns out the outermost electrons, in this case, 3s2, are the key ones. And what are the outermost electrons? Those are the valence electrons. How did you like that transition? And you should know what is a valence electron. And the valence electrons are the outermost electrons, or is the outermost electron of an atom of an element. And they're the most important ones. Dr. White loves messing with valence electrons, and I have. And now, 2 points each. How many valence electrons do each of the following have? Well, how do you figure out the number of valence electrons for hydrogen or carbon? You look at the periodic table. And as you can see in the periodic table on your screen, if you look at the top of each column, you'll see a Roman numeral and a numeric numeral. I think that's the right way of saying it, a regular number. And that tells you for every element in that column how many valence electrons it has. And if we look at hydrogen right here, up above is 1. If we look at calcium, which you need calcium cations for strong bones, but the valence electrons calcium are 2. And carbon is 4. All right, I'm going to not take away all the fun. How many valence electrons does oxygen have? Your turn. Time's up. Here's oxygen. Look up here, and the answer is 6. And a couple of you were right who happened to decide to put it in chat. Thank you. Oh, let's do another one. How many valence electrons does bromine have? And hopefully you learned your elements, the ones I asked you to learn. And somebody's got the right answer. And the answer is 7. Bromine, Br, 7. Now, how many valence electrons, one of my favorite elements, because I used it a lot, does argon have? Looking around, seeing all the smiling faces, see a bunch of people have gotten it correctly. Argon, chemical symbol Ar, and it's got 8. And that's how you find valence electrons. Now, when we're talking about valence electrons, and I don't see it in the problem set, so let's do some of our own. Now, one thing that I should clarify, because there was a good question one of your colleagues had, when we talk about drawing Lewis structures, when you draw the Lewis structure, listen carefully, for an element, you only have, you do 1 dot on each side, and then you double up. For, and this is important, an element, you have never more than 2 dots on the side. And each side should have 1 dot before you double up. Now, for a molecule, those rules don't apply. How do you like that? Don't apply. That's a big no. Fooled you there. It's a big no, 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 no. And therefore, remember that. Again, I'll repeat this. For an element, the Lewis structure, you have maximum of 2 dots on one side, and you put 1 dot on each side before you double up. For a compound, a molecule, the Lewis structure, those rules aren't valid. You can have more than 2 dots on a side, and some sides have 0 dots. And again, that's for a compound, otherwise known as, in my class, a molecule. So let's go look at some. Now, carbon, first of all, how do you do the Lewis structure? Remember, Lewis structure is for valence electrons, the outermost electrons. And therefore, I have to go to my periodic table and find carbon has 4 valence electrons. And now I know I'm dealing with 4 valence electrons. I put the chemical symbol and then 1 on each side. If you had one side with none and one doubled up, I'd mark that wrong. Now, I'm going to let you do the next one and I'll help you out. Nitrogen has 5 valence electrons. So it's your turn to do the Lewis structure for nitrogen. You people ready for some really bad humor on a Friday morning? Oh no, I'm seeing dots in front of my eyes. Oh, that was even bad for Dr. White. Yeah, I won't say that again. See how cruel I am? I make you have to suffer through all my humor. All right, let's do the Lewis structure for nitrogen. How do you do that? Write the chemical symbol. From the periodic table, you found out from looking at the top of the column, nitrogen has 5 valence electrons. Put a dot on each side before you double up. Now, organic chemists like to put the pair of valence electrons of nitrogen on the top, but I'm going to have to force my hand to do it. Come on, hand, you can do it. I'll do 1 dot on each side. And now, oh, this doesn't look right, but I'll do it for you. That's also acceptable. So actually, there are 4 different ways you can draw the Lewis structure for nitrogen. And that is one side has 2 dots and the other 3 sides have 1 dot. Oh, let's do one more. Practice is good for your grade, which I think you'll like. And if we do chlorine, you'd see it has 7 valence electrons, and it's your turn to do it again. Boy, am I being nice today, sharing all this fun. All right, I think everybody's done. Let's do it. Well, chlorine, the chemical symbol is Cl. And you put 1 dot on each side before doubling up. I have 4, I have 3 more to go. Number 5, number 6, number 7. And this is one way of drawing the Lewis structure for chlorine. There are 4 others. Another one could be this one. And there would be 2 more. 3 sides have 2 dots, 1 side has 1. And that's how you do Lewis structures for elements. Now, let's do for structures. But before we do that, I should have put the questions differently on here. Let's talk about covalent bonds. Covalent bonds, remember, are sharing pairs of electrons. And you should know the name and the number of pairs of electrons each of the 3 covalent bonds have. And you don't have to turn on your mics now, but it's class participation. Everybody, what's the name of the first covalent bond? Single bond. Everybody together. You don't have to turn your mics on, but say it out loud at home. If we were in a classroom, I'd be asking you to yell it out loud. What's the second covalent bond? Double bond. What's the third? Triple bond. For those of you who know baseball, when you get a single, you go to first base. And a single bond, covalent bond, has 1 pair of electrons. Double in baseball, you go to second base, and a double bond in covalent bond has 2 pair of electrons. And finally, a triple bond baseball, you go to third base, and that means triple bonds have 3 pairs of electrons. So let's do it again. What are the 3 types of covalent bonds? Single bond, double bond, triple bond. Remember, single bond, 1 pair of electrons, double bond, 2 pair, triple bond, 3 pair. Now that we've got that, let's look at how do you draw the Lewis structure for the following. And the first one is one of my favorite molecules, water. Why? Because that helps keep me alive. And that's a good reason to like it. And helps keep you alive too. So if I were to ask, continuing, draw the Lewis structure for water, what do? Well, first of all, you have to figure out hydrogen has 1 valence electron and oxygen has how many? 6 valence electrons. Now, if I have my oxygen, which is going to be in the center, because that's the only way you're going to make this work, remember the octet rule. Atoms of elements lose, gain, or share electrons to have an octet. The one exception to the octet rule is hydrogen, and its octet is 2 electrons. Again, hydrogen's octet is 2. Every other element will want to get 8 valence electrons. So I've got 2 hydrogens. Each one has 1 electron, valence electron. And this hydrogen says to this oxygen, I've got 1 valence, you've got 1 valence electron, let's share. And they do. And they form a covalent bond. What kind? 1 pair of electron. That's a single bond. And the other hydrogen, because there are 2 of them, says to the oxygen, I've got 1 valence electron, you have 1, let's share. And that's the single bond. So the next time you're Zooming with friends, and hopefully in the near future, we'll be all face to face, but the way they're talking, it might be a while. And you'll be able to see when a friend of yours is drinking water like this. Oh, that is good. You say, do you know you just drank a molecule that has 2, not 1, but 2 single bonds? Don't do that. Friends don't like to hear chemistry when they're drinking water. Family members too. All right. So that's how you do it. Now, let's look at this one. Well, here, chlorine and nitrogen, this is called nitrogen trichloride. Let's see how we do that. Nitrogen has 5 valence electrons. Each chlorine has 7 valence electrons. And if I draw the Lewis structure of chlorine, of nitrogen, there it is. Notice it has 1, 2, 3 unpaired electrons. And chlorine has 7. And something I just remembered I forgot to do, let's go back and look at this, because I forgot to do something bad, Dr. White. Now, if we look at the oxygen, how many electrons are around it, both its own and shared? If you look in the red box, count the dots, and you'll see 8. And that's because now oxygen is happy. You know elements, atoms of elements can be happy or sad. And it's happy because it has 8 valence electrons, or its octet. Now, if we look at hydrogen and all its own and shared electrons, each hydrogen. How many does it have? 2. And it's happy. Why? Because its octet is 2. That's the one exception to the octet rule. Now, let's get back to nitrogen trichloride. Now, each chlorine has 1 valence electron, and it says to nitrogen, each one, I've got 1 valence electron, you've got 1 unpaired valence electron, let's share. And they do. And the non-bonding electrons around the chlorine come along for the ride. And the second chlorine atom does the same thing. And the third one does the same thing. Let's share. And now if we look at the chlorine, and it's the same for all 3, how many dots do you see? 8. It now has its octet and it's happy. If we look at the nitrogen, oops, how many dots do you see in the blue box? 2, 4, 6, 8. It has its octet. And that's an important check to make sure you did this right. Let's do the next one, which is HCN. And hydrogen has 1 valence electron. But before we do this one, hold on. Let's do something more interesting first. Oxygen. Right now, I hope all of you are inhaling and exhaling. And when you inhale, part of the air you're breathing has oxygen, O2. How come it's not O7? Well, let's look. Each oxygen, as we saw earlier, has 6 valence electrons. So if I have 2 of them, same thing. And this oxygen right here says to this one right here, I've got 2 unpaired valence electrons. You have 2 unpaired valence electrons. Let's share. The non-bonding pairs are still there. They come along for the ride. So I have my 2 oxygen. I have not 1, but 2 pair of electrons. And then I have my non-bonding electrons. And what kind of bond is this between the 2 oxygens? And answer is a double bond. Double bond, 2 pair electrons, triple bond, 3 pair, single bond, 1 pair. And now I'm going to let you do one on your own because I want to share the fun. Now I'll help you out. Hydrogen cyanide, HCN. Hydrogen has 1 valence electron, carbon 4, nitrogen 5. Now I will tell you the carbon has to be in the middle for this to work. Have fun. And when you're done, give me a thumbs up. This one's a little more challenging. So challenging, I bet later today when you're talking to some of your friends, they'll say, oh, you should have seen chemistry today. Dr. White was so mean to us. He made us work real hard doing electron configurations, valence electrons, in a very explosive lab. And it was fun. I hope it was for you. All right. I think everybody's just about done. Let's do this. How do you do the valence, the Lewis structure for hydrogen cyanide? Well, hydrogen has one electron, carbon has four, and nitrogen has five. And the hydrogen looks at the carbon and says, I've got one valence electron, you've got one, let's share. And it does. Now that takes care of that electron. And the carbon looks at nitrogen and says, I have three single valence electrons. You have three single valence electrons. Let's share. And three times two, each one has three, are six or three pair. And the non-bonding electrons on nitrogen are still there. And this is the Lewis structure for hydrogen cyanide. And let's find out, did we do this correctly? Now, here, hydrogen has its octet of 2. That's good. Here, carbon, how many dots are there? 2, 4, 6, 8. It has 8. It does have its octet. And finally, I'll use red again. If we look at nitrogen, it also has 8 valence electrons. So everybody's happy. Now, next question is, what kind of bond exists between carbon and nitrogen? And you count the number of pairs of electrons. 3 pairs. That's a triple bond. Now, next one we'll do is sodium hydroxide. But before I do that, I have to teach you something or remind you of something really. Everybody, pay attention. This is important. If you look at the alkali metals, that's lithium, sodium, potassium for this class, and the alkaline earth metals, magnesium and calcium, the first and second column, the first one, not including hydrogen, because that's not an alkali metal, but the alkali metals and the alkaline earth metals always form ionic bonds. They are never in a covalent bond, at least that I know of. And for a number of years now, I've asked other chemists I know who know this stuff as well as I do, and they agree the alkali metals and the alkaline earth metals never form covalent bonds. They're only in ionic bonds. So what does that mean? Well, let's look at draw the Lewis structure for sodium hydroxide. And sodium hydroxide, the old ancient name for this chemical, and still is used at times, is lye. If you've ever heard of lye soap, they use sodium hydroxide to make it. Well, sodium has one valence electron, Oxygen has 6 valence electrons, and hydrogen has 1 valence electron. Now, I told you sodium never is in a covalent bond. Therefore, what ion does sodium form? And we already did this. It forms a +1. However, oxygen has 6 valence electrons. Hydrogen has 1, and the hydrogen says to the oxygen, let's share, and they do. So if we look here, hydrogen has 2 valence electrons. If we look here, oxygen only has 7. What's wrong? Well, where did this electron that sodium had go? It goes over to the oxygen like this. Now, oxygen has an extra electron. One way of showing it, I like putting in brackets. You don't have to, but I like to, is it goes to the oxygen. And now you have between the sodium cation and the hydroxide polyatomic ion, an ionic bond. Between the oxygen and the hydrogen, you have a covalent bond. Remember, alkali metals and alkaline earth metals always form only covalent ionic bonds. Let me say it again, only form ionic bonds. And your turn. This is potassium hydroxide. Both of these chemicals are widely used, and a lot is made yearly, millions of pounds in the United States. And KOH, potassium hydroxide, had the old name of potash because it was first discovered in the burnt wood underneath your cooking pot when years ago people cooked over a fire with logs or wood. So why don't you draw the Lewis structure for potassium hydroxide? And when you're done, look up and give me a thumbs up if your camera's on. If it's not on, just give me a thumbs up. See, a number of people are starting to do that. All right, I'll give you 10 more seconds. 5, 4, 3. Boy, I went fast that 10 seconds. Time's up, and let's look at this. All right, now, potassium is an alkali metal. Therefore, it's going to form this cation. Oxygen has 6 valence electrons, hydrogen has 1, and it will share it with the oxygen. And where did the electron go that made this cation? It goes to the oxygen. And KOH, similar to sodium hydroxide, NaOH, has an ionic bond between the potassium and the polyatomic ion hydroxide. And between the oxygen and hydrogen, there's a covalent single bond. And if I look at the clock, it's time for Dr. White to take a 5-minute break. Go stretch. When you get older, you'll find out about that. But anyways, I'll see you in 5 at 9:55. right, ring, 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 ring. Time to come back from recess. How many of you remember in grade school? I don't know if you had it, like in first, second, or third grade, we'd be let out for recess every once in a while. I forgot when, in the morning, in the afternoon. You go out and play a little, and then they'd sound some bell or something. Time to come back in. Boy, that was a long time ago. All right, let's get back to chemistry. Now, let's do one more of these, and that is the Lewis structure of an element, of a molecule. And let me give you this one. And actually, let me write it down here again, give myself more room. And sodium has 1 valence electron, carbon has 4 valence electrons, and nitrogen has 5 valence electrons. And I see I have a question. Either I didn't do my see what happens when I don't ask, if you can see it. Zoom says you should see it on the screen. And now do you see it? I should ask my thumbs up, people. Oh, okay, thank you. All right, now let's do it again. Instant replay. Draw the Lewis structure for sodium cyanide. Sodium, 1 valence electron. Carbon, 4 valence electrons. Nitrogen, 5 valence electrons. Your turn. And if we were in a classroom, I'd say, when you're done, look up and smile. And I see all these smiling faces, but you don't have to smile if you don't want to. It's a free country still. Ooh, I forgot to tell yesterday's lab. Monday after class, for those who want to stick around, learn more about Dr. White, I will show you a picture of me and my 3 favorite girls, long gone but not forgotten. 3 of my sister's dogs, so I like to play with, for those who have dogs. I think you'd like to see them. That's Wendy, Misty, and Janie. Oh, I miss them. And when you're done, give me a thumbs up. All right, I think, anybody need more time? Yell out. Oh, I don't hear any, so let's do it. All right, now, as I mentioned earlier, whenever you have an alkali metal like sodium, potassium, or lithium, it always forms a cation to be an ionic bond. And the cation sodium always forms is a +1 cation, which we learned earlier how to figure that out. Now, carbon has 4 valence electrons, nitrogen has 5, And notice over here, carbon has at least 3 unpaired electrons, valence electrons. Nitrogen has 3, and the carbon says to the nitrogen, hey, I've got 3, you've got 3, let's share. And they do. The non-bonding electrons of nitrogen is still there. Carbon has 1 more. Sodium is a plus. But where did this electron go? It went here to carbon. And now carbon has an extra electron. And therefore, in sodium cyanide, between the sodium, and this is called the cyanide polyatomic anion, there's an ionic bond. What type of bond is between carbon and nitrogen? I'll give you 3.2 seconds. Go. Time's up. A triple bond, because of 3 pairs of electrons. And that's everything you want to know about Lewis structures and elements, and now molecules. Let's move on. And the last thing I'd like to talk about, which we talked about, give an example of a molecule that can hydrogen bond. Remember, hydrogen bond is the weak, I see a question, so hold on. All right, someone asked about ammonium chloride. So this one, let's do it. Now this one I'm debating would I ever put on a test, but let's do ammonium chloride. And nitrogen, 5 valence electrons, and hydrogen, 1 valence electron, and chlorine, 7 valence electrons. Now, nitrogen has 5 valence electrons, and this is a little trickier. Hydrogen has 1 valence electron, and notice it's NH4Cl. And here, this hydrogen, and this hydrogen, and this hydrogen go like that. Now, we have this hydrogen has a valence electron, and it can give it up to the chlorine so it can share with this. Since this should have 5 plus 4 valence electrons, which would be a total of 9, but it has 8, it's given up an electron. And that makes it a positive charged polyatomic ion. I probably wouldn't put this on the test. Now, chlorine normally has 7 valence electrons, and the extra electron from here goes over here, and chlorine now forms the chloride anion. So between the ammonium cation and the chloride anion, there's an ionic bond, and here we have covalent bonds between the nitrogen and the hydrogen. And that's how you do it. Come to think of it, I probably wouldn't put it on the test, and I should have taken off the problem set. Bad, Dr. White. You're welcome. Remember, all questions are good questions in Dr. White's universe, including my class. All right, now we're talking about hydrogen bonding, and you should know that molecules that have oxygen, nitrogen, or fluorine that has a hydrogen on that oxygen, nitrogen, or fluorine can hydrogen bond. An example of a molecule, probably the most famous, is water hydrogen bonds. Ammonia does that too. Alcohols, which have oxygen with a hydrogen on it, can, And let me move this down, hydrogen fluoride. So best example would be water or ammonia. Alcohols and hydrogen fluoride are also good. And that's the problem set. Any questions before it's lab time? Well, in that case, it's time for a lab. And today's lab, let's open it up. And you can download this from Blackboard. Everybody see moving electrons from shell to shell on your screen? Thank you. All right, today's lab is moving electrons from shell to shell, also known as the flame test. And what do we mean by moving electrons? Well, electrons are in certain shells and subshells. If you add energy to them, the right amount, they'll move to the next highest or even higher subshell and shell. How do you add energy? One is by heat. Now, how can you generate heat? With an explosion or with a flame. Another way of adding energy is with ultraviolet light. How many of you have heard you go out in the sun, if you don't have proper protection, you can get skin cancer from the ultraviolet light from our sun? That's because ultraviolet light is very high energy. Now, it's time for a special surprise from Dr. White. Hold on while I get it ready. Hold on while I find it. It was here the other day. Ah, here we go. This is not the surprise. All right. Let me do this. Thumbs up, people. Can you see YouTube on your screen? All right. Let's go full screen. And what you just saw were electrons moving from shell to shell. Now, when there were an explosion from the fireworks, that gave off a lot of energy that forced the electrons, the valence electrons, to move to higher shell and subshell. Once it gets away from the heat or the energy, it says, the electron, what am I doing here? I want to go back home. And it does. It comes back to its old subshell and shell. Well, when it comes back, when it was out here, it had all this energy that forced it there. When it comes back, it gives off that energy. And one form it gives it off in is light. And because the shell and subshell movement for certain elements is fixed, you see different color lights depending on the element. Now, today's lab, you'll be, instead of doing fireworks, we're going to be, I'll show you in a little while, you'll be using Beyond Lab Z to put different chemicals into a Bunsen burner. And a Bunsen burner, if we were in the lab, you'd be using it. I'd be showing you how to use a Bunsen burner. I'd tell everybody with long hair to pull it back because hair is very flammable, and you'd have fun. Now, quick Dr. White story. When I was your age, wow, that was a long time ago, after college and grad school, friends of mine, guys I knew, we used to go downtown Chicago to the old 4th of July uh, fireworks. That's before they had the music along with it. I don't like the music with stuff. It took me a while to find that YouTube without music with it. My personal opinion, fireworks are to be enjoyed without music because you want to hear the explosions and to feel them. Anyways, that's what you do. Let's look at today's lab. Now, as I said, electrons are located a specific distance from the center nucleus of an atom, and they're in shells and they have subshells. And when you add energy to an atom by heating it or shining a light on it, which we'll talk about, that happens to put the electrons in a higher energy level, which is unstable. And once the form of energy, once that happens, when it loses the energy, it goes back to the original subshell and shell and gives off energy. One way is light, and you see different electrons giving different amounts of energy. In this lab, you'll be heating different solutions of molecules and in the flame of a Bunsen burner. And this is called the flame test. And this is also a way of identifying unknown compounds, which you sometimes see in CSI programs. Now, here's some more video if you want to watch, and you'll be doing this. Now, turns out organic molecules, which are mostly covalent, don't do a good job of flame test. But ionic molecules, which have cations and anions, ooh, look out. That's what you were seeing in those fireworks. Now, question is, if you have a molecule with a cation and an anion, which causes the color? Both or only one? Good question. Thank you, Dr. White. And today's lab, you'll be investigating that too. Which ion, the cation or the anion, in an inorganic ionic molecule causes the color? How many of you have ever cooked noodles or rice in boiling water and you add some salt to it? And once in a while, if you're not paying attention, a little will boil over and get in. If you're using a gas flame underneath on a gas oven or stove, and you see the blue flame turn yellow. What's causing that? The sodium chloride. I gave something away. But anyways, one of the important things when you're doing research, which you will be doing, don't get scared, it'll be fun, is you only change one variable at a time. So if we're trying to find out, is it the cation or the anion that's causing the color when you heat up an ionic molecule, we're going to do a bunch of different cations, but keeping the anion the same. And then we'll do one where keeping different cations, but keeping the anion the same. And you'll be able to find out, that's one of the questions I asked in this lab, which causes the color, the cation or the anion? Well, we'll find out. Now, in this lab, I'll show you in a second. Let's go through the written part, then we'll switch to Beyond Lab Z. You'll open it up, go to the inorganic lab, which you've already been in the higher ed for chemistry. And what you'll do is put the test tube on the ring stand, and you do this by just double clicking on the test tube box. One of your colleagues' daughters taught me that. And then upper right hand screen will now be visible, and click on the chemical, click on the Bunsen burner. I'll show you this in a second. And then look at the color in the little window in the upper left and record your observation. And then the right hand part of the screen, I found out from the same daughter of one of your colleagues in the other lab section, the waste container, if you double click on the circle, right circle, I'll show you this when we get to Beyond Lab Z, puts the test tube in there. You don't have to drag it over and try and orientate that. Now, here are the different mixtures. For sodium chloride and Beyond Lab Z, it's called Na plus on the bottle. This is KC, so on. By the way, I made a mistake here. This should be, I think, a 3 in, somebody said. But anyways, one of the interesting things in real life, and I have done this with 1211 and also at the other school, this lab that I wrote myself, when you do ferrochloride, you'll find out that not only do you see a color, but you also see these really pretty sparkly things, just like a sparkler from the 4th of July. This is really, now, since they don't have us, isn't available in the Beyond Lab Z, same cation, different anions. If we're in the lab, this is how you would do it. Since we can't do it, here's the data. I've already put it in for you. And then just to have fun, in Beyond Lab Z, why don't you try mixing these two together and doing the flame test and see what happens. And in real life, students ask me, can we do our own? And so you can do your favorite pair also. Have fun. Now, another way, and here's how you do it. Another thing is flame tests are used to identify unknowns. Now, Beyond Lab Z is not really set up for this the way I'd like it to. So this is if we were in the lab, you do this. And then for compound unknown A, am I original or am I original, and unknown B, I've helped you out. And you're going to have to, in later questions, identify based on your results from table 1, the earlier experiment, what is unknown A and what is unknown B. Now, the other way of moving electrons is adding other types of energy. And one of those is ultraviolet light. And also regular light will do it, but ultraviolet light has more energy than white light you're using now and wherever you are. And how do we do that? Glow in the dark paints. And what I did for this lab, which I can't do now but on Beyond Lab Z, is I made up a bunch of index cards with 3 stripes. And they all look this sort of like white glue color. But when you shine light on them, you can see a color that's glow in the dark. Now, when we do this in a lab, well, I'm not going to shut off the lights because other people are doing other things. So I came up with this real expensive glow in the dark card viewing device, otherwise known as jewel paper shopping bags. And you stick the card in there and you look. Now, on real life, I'd have 3 lines on there labeled A, B, and C. And I have different cards where Dr. White's sneaky. I have different orders of the lines, and you'd have to write down the card number. You don't have for this. You put it under a UV light, and then you put it in a bag and watch. Now, different colors, different electrons Some come back slowly and give off light for a long time. Some go whoop, real fast. And you're asked to time that. And since we're not going to sit around all day, because certain colors take almost 24 hours before they stop glowing, I told students in the lab, if it's greater than 3 minutes, put a greater than 3. And I gave you the data for this one. And here's if we were in there, you do the UV lamp and only put in 3 seconds worth of energy. And if you did, line A would be red, B is blue, C is green. A stopped after 20 seconds, B, blue stopped after 2 minutes, and the green was still active after 3 minutes. Actually, this takes hours to stop, which students don't have in a lab. And here are the questions. All right, give me a second while I open up Beyond Lab Z. Actually, more than 1 second. And you'd open up the chemistry lab, which you know how to do. And the virtual lab here, you'd click on inorganic. Does everybody see the Beyond Lab Z? Thank you. Now, here's how you do the lab. It's real simple. It's a lot of fun. You can go back and do as many. Here's the test tube. I'm going to double click on this and notice, oh, the test tube's already in the holder. Let's do, because I already gave it away, sodium. You find the sodium bottle up in the upper right. You click on that and notice there's now a liquid in there. Now, in the lower corner, see where it says, if I hold my mouse over there, flame, click on that. And you'll see the picture up here. Oh, look at the yellow color. It's formed a yellow flame. If you want to do it again, have fun. And it forms a yellow flame. And you'll do the, and now, if you want to do next one, I had pick it up, but if you look in the lower right corner, the little red container with the white circle, put your mouse in there and click once, and it's done. And now you double click here and pick another one. And I'm not gonna, what's one I didn't have you do? Well, anyways, you get the picture, and that's how you do it. Any questions about the lab? Remember, this lab is due next Friday. The lab we did last week is due today or tomorrow. Make sure you get them in. Now, what I'm going to do now is, for about the next 10 minutes or so, is I'm going to send you out. All right, is it SR plus 3, plus 2? I think that's what I made. Let's go back here. It's a plus 2, that's the one. And that, use the SR plus 2 and as strontium as opposed to that plus 3 that I made a mistake on. Like I said, I don't walk on water. Dr. White does make mistakes. All right, what I'm going to do is, let's see if there are any more questions. You're welcome. And thank you for finding that mistake of mine, that Dr. White. Now, right now, I can just random order, send you out the breakout rooms. Will take about 10 minutes. When you're in a breakout room, say hello to your colleagues, learn about them a little, share as much as you want or whatever. But I will ask you, when we go to a breakout room, turn on your webcam, and I'm going to go visit some of them. So let me set it up. Hang in there for about a minute. Oop. I'm going to open all rooms, and in about 10 minutes, let's get back. You're still going to get out. So I think it's your lower right-hand corner. Go to a breakout room. Everybody, come on, you can do it. Go to the breakout room. This is anonymous, so don't worry. I won't know, and you won't, anybody else won't know how you answer, but want you to answer the following question. All right, well, I think just about everybody answered. So it looks unanimous. You people enjoyed going to breakout rooms. So in future labs, maybe not everyone, but we'll do that where I mix you up unless if somebody has a better idea, you want to form your own little groups, up to you, as long as everybody gets included. I don't want anybody felt left out. That's not nice. And with that, I'm done for today. Got you out early. We had a wonderful morning. I hope you enjoyed the fireworks. I hope you enjoyed doing the lab. And I'll see you on Monday. Have a nice rest of the week. I'm going to stick around for a couple minutes in case you have any questions for me. And with that, I'll say, Gang gesund, goodbye, or I'll do it this way. Bye.